Hi, I'm back with an update for my term project on the Jeffcott rotor. In the last video, I introduced my overall program and ran a few simulations to try it on for size. In this video, I'll be doing a bit of a deeper dive on a single scenario and showing you some interesting stuff as we play with the angular velocity. First, I'll go through a few additions to the code. This line here takes the x and y displacement of the rotor that we've calculated up here and calculates essentially its spin radius. It's fairly simple, but it gives a good visualization of how the rotor is moving. In these lines, I've calculated and plotted u, which Jeffcott referred to as the ultimate amplitude of vibration at the elastic center. So for today's model, we'll be using a mass of 1, an offset distance of 0.05, no damping, and an elastic force of restitution of 0.1. I've moved the angular velocity down here because I'm going to change it as we go along, and it's a little easier to keep things separate when you're trying to do that. I've decided to go undamped today to really show the effect of changes on the angular velocity, or changes in the angular velocity. Okay, so let's go back to this equation for the ultimate amplitude of vibration. Assuming all the physical properties of the system are locked in, right? The mass, the offset, the damping, the elastic force of restitution, this amplitude will only be affected by the angular velocity. So if we plot this, we get the following. Essentially, this amplitude is fairly level, but spikes to infinity at an angular velocity of approximately 0.32. This is actually the value of k, or whirling speed, which can be approximated as the square root of the elastic force of restitution divided by the mass, or around 0.316 here. So what exactly happens to the displacement of the rotor as the angular velocity approaches and then passes the whirling speed k? We can get a quick idea by running a few simulations. So at 30% of k, let's see, right, there's nothing too special here. Motion is about as stable as it gets for an undamped system. If we look at 70% of k, we get pretty much the same thing. Nothing too interesting. However, when you run it at 90% of k, you start to see something a little more interesting, right? The displacement has gotten much larger than it was previously, and you see this beating phenomenon also, which is said to occur as the forcing vibration approaches this whirling speed. So then what happens if we have an omega exactly equal to k? Right, so as you can see here, this correlates exactly to this. So we see this displacement become increasingly bigger, and if we took this out to even 10,000, right, we would see the same thing. It doesn't stop. So that goes essentially to infinity. Of course, that's because it's undamped with a damping coefficient of, say, 0.001, if we run this again. And then, let's see, bring this out to about 3,000. Then you can see that this doesn't become infinite, although it does become increasingly large. And you can see that here in this plot of u as well, that it only goes up to around 16, which is still huge. But that's the effect of having a damping coefficient in this model. Alright, and then going back to undamped, and then edging just past K to 1.01 K, and running it. You can see, and you can see it better if you bring it out to about 3000 again. You can see that the infinite phenomenon is gone, and we're back to an extremely big amplitude and the beating phenomenon. And if we bring this even further past K, you'll see that it essentially resumes normal function here. And right, so that is my update for today. Thank you for watching.